Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone, those who are in the room and those who are attending this talk remotely. Good evening to those who are going to watch the recording this evening. It's my pleasure to present Nikolai Gavovich, who took his master's degree in Queen Mary University of London in 2002 and defended his PhD in Imperial College London in 2006. Nikolai has been presenting here, I think, in 2008, some results from his PhD thesis, and today he is going to present a multi-microphone reverberation in intelligibility estimation in speech processing. Without further ado, Nikolai, you have the floor.
Thank you. Thanks, and thank you for those standing up and those watching remotely. Yeah, basically, as the title suggests, there are two separate topics, the dereverberation and the intelligibility, and they sort of represents the two eras of my life in this field. So one is more from my PhD time, and the other bit is something that I've been working on more recently. So to begin with this, I just wanted to sort of have an overall look at what we're trying to solve. And basically the key idea is that we have some wanted speech signal somewhere produced by a talker, and we have a recorded sound at the end. And the idea is that this wanted speech should be understood by a listener at either a different time or different location. And in the meantime, this wanted speech passes through a lot of things. You have an acoustic channel, some additional noise due to other sources, possibly with their own channel effects, microphones, amplifiers, maybe some codecs, so on and so forth, and you get there. And by the time you've got there, there can be a lot of things happening, which in general, if you have a human listener, they would reduce the intelligibility. So what was tried to be conveyed by the talker is not really understood by the listener. There's also lower quality of the signal, so it's not that pleasant to listen to. And then I have this productivity thing in question marks, which is something that people have worked with related to the project I was working on now, to try to see if productivity of, say, for example, a transcriber is affected by noise and noise reduction algorithms. But there's no sort of conclusive evidence of any of that yet, so that's why I have the question mark. Or you can have a machine listener at the other end, like speech recognition or speaker identification, something. And they also perform badly once you have this scenario. So as I said, the talk will be in two parts. In the first part, I'll mention about multi-microphone dereverberation, one method which is a source filter model-based method, and one which uses blind channel identification and inversion. And in the second part, I'll talk about intelligibility estimation. And this is mainly subject-based intelligibility estimation, so you have subjects in the loop. And I'll talk about how we use these methods for evaluating speech enhancement algorithms. So let's just quickly go over what the problem of dereverberation is that we're trying to solve. We have some speech signal, S of n, that is produced in a room. Actually, before I continue, if you have any questions, please interrupt me, because there's quite a few different topics, and if you wait till the end, it gets messy. So we have this speech signal S of n produced in some reverberant room, and it's observed by a bunch of microphones, and the talker is at some distance from the microphone array. So we formulate this as the observed signal with the microphone is the convolution between the speech signal and the room impulse response, plus some additive noise. And the aim of the reverberation is to find some estimate of the speech signal S possibly delayed or attenuated. It's not a problem. And in most cases, the dereverberation is a blind problem, so we don't know anything else but X, so just the observed signal. So we try to do everything based on that. So I think there are generally three classes of ways to do dereverberation, three classes of methods. One is beamforming, where you have some kind of array of microphones and you do some processing to all these microphones and you sum them in a way to try and form a beam in the direction of the talker that you want. And beamforming is obviously a multi-channel, multi-microphone approach exclusively. Then there's something called, or I'd like to call, speech enhancement methods, where you may use some model of the speech signal or and then modify your reverberant speech observation in a way so that you better represent this, this model. Or you can have some model of the impulse response and then use that to process your reverberant observation. An example of this is spectral subtraction type of dereverberation methods. And finally, you have blind system identification and equalization, where you would try and actually estimate the impulse responses and then form some inverse filters based on this. And of course, you can have a combination of all these things to form methods. So the first method that I will talk about is based on the speech enhancement methods, where it uses a model of the speech signal. It's quite a straightforward method, really. It starts by looking at the LPC formulation of speech. So if you have a clean speech signal, you can write it in terms of a linear predictor, like this, where A are the prediction coefficients and E is the prediction residual that you get from this. And you can have a reverberant observation, which is formulated in the same way. And then what you can look at is the relationship now between the two different parameters of LPC. So what is the relationship between the coefficients A and B, and what is the relationship between the prediction residuals of the two. So here is an example of a bit of voice speech, which could be quite familiar. So you have at the top left is a clean speech signal, some reverberant speech signal. Here is and here are the residuals for the two signals. So you can see this one is probably the sort of familiar structure where you have peaks in the residual that approximately represent the instance of glottal closure. And you have the reverberant residual. It becomes messy because this structure is destroyed due to the reverberation. So reverberation affects the residual quite a lot. But on the other hand, it's been found by several people generally that the LP coefficients are much less affected by the reverberation. So looking at these things, you can think of a way of doing the reverberation by three steps. You do LPC analysis of your reverberant observations. You get a bunch of residuals. You process the residuals, and then you use the LPC coefficients that you got from the reverberant speech, and then you resynthesize the speech. So one of the advantages of this is partly that you have much simpler structure of the clean speech residual, and you know what it is, so you can maybe take advantage of that to some extent. And yeah, it assumes that the coefficients will not be as affected. So the way we looked at this thing is something called, something that combines spatial and temporal averaging of the residuals. So this is some motivation behind what the algorithm that I want to talk about is doing. So again, if you have a clean speech residual and you have a reverberant speech residual, you see that the peaks that are from the original residual are kind of obscured and it's difficult to see where they are. If you were to take a microphone array and get the residual from the output of just the delay and sum beamformer, you start to get a much better result of the structure, right? So you can see these peaks much clearer, but there's still a lot of rubbish in between. So the structure between the peaks is quite far from this thing. So the first observation is that if we do spatial averaging, we should be able to identify these instances of glottal closure.
The last one is running a delay sum beamformer and then doing LPC, or doing LPC in each channel and then averaging the...
No, this is doing a delay and sum beamformer and then doing an LPC. And yeah, the other observation you can see is that actually the signal between these peaks is pretty similar, so it changes quite slowly, whilst the output of the beamformer residual seems to be much less correlated in between. So the idea could be that you could segment these larynx cycles between the peaks and then do some kind of moving average operation, so that you will take this one and average it with its neighbors. It should reduce the effects of these and get back to this structure a bit more. So that's really the idea behind this approach. And in order to do this larynx averaging, you need to be able to identify these peaks. And for that, I've used something called DIPSA, which is it's very robust for identifying GCIs in clean speech, and at the output of a beamformer, it performs pretty well as well, satisfactory enough. And also, when you do the averaging of these larynx cycles, you don't want to include the actual peaks in the averaging, because they're quite sensitive. So if you distort some of these peaks, you can hear it in the resynthesized speech afterwards. So to avoid this, basically what you can do is use some kind of windowing function around the cycle. So if you take, for example, this is what I was using, is just a time domain Tucky window. You can center it within the larynx cycle, and that would exclude, basically, it would exclude the glottal closure instance with some margin on the sides, so that you can have some room for errors. So then you basically segment your larynx cycles, average across them without the peaks, and put together the peaks. That's what this does. And in the second step, what you can do is, instead of actually using these averaged larynx cycles, you can try and calculate an inverse filter based on your original larynx cycle and the one that you've just averaged, and you update this filter slowly. So in this way, you can partly reduce the sensitivity of GCI detection errors, but also basically this whole thing that I've described mainly works for voiced speech. And when you come to an unvoiced segment, you can continue using this filter, because it should be a relatively good estimation of what happens to reduce the reverberation. Yeah.
So is the averaging done over a fixed number of windows, or are you doing that adaptively based on how much the residual is brought down?
I do it as a fixed, so normally sort of 1 or 2 larynx cycles on each side of the one that you're looking at.
And the other question I have is that, I mean, it seems like, a lot of times, if you have a reverberant environment, right, that the peaks are in the cycles and the the larynx signature is being kind of jittered around in time a little bit, right? Because there's reflections that are coming at different times, so you see like this return reflection a little bit higher, and I worry to some degree that is this averaging time aligned in any way beyond the glottal peak? Like, do you try to do some alignment within the blaring signature as well after you've done the windowing, or is it?
No, it's just aligned with the peak itself. Yeah. I see what you mean, because you normally wouldn't have exactly the same.
Right, and you might just be zeroing out signal by just having slight shifts in the.
Yeah, but you try to basically align them with the peak, and also you keep the original peak position. That's why you don't include the peak in the averaging process itself.
Right.
So you just average whatever is in between. So. Yeah, I just found that works best anyway from the different ones that I looked at.
So G is just a filter that approximates the difference between E hat and E bar?
Yeah, exactly.
And then that's what you actually use to get this.
That's what you actually apply,
yeah.
It's just, partly to know what to do when you have unvoiced speech coming, for example, because, and also it reduces the errors that you get. Yeah, the artifacts. So this is a diagram basically of. Sorry.
Yeah. So I mean, what does G actually do? Is it basically a high pass filter, or what?
G is just it's a least squares match between.
What does it come out to be?
Well, it should be something which relates to the inverse filter of the room transfer function to some extent. It's not really a high.
But you're operating much smaller.
Yeah, it is. Yeah, exactly. So it's not going to be. It's not going to be enough to invert the full thing, but it will be kind of a very smoothed version of that. If you just have a very small size, right? It will.
And then the other thing is that filter is now being applied to the peaks as well. It's being applied to the whole signal.
It's applied to the peaks as well. Yeah, it's applied to everything.
So there, I wonder if you might have some, because there is something like you can imagine there might be certain pathologies, and I'm not saying this necessarily happens, but you can imagine certain pathologies where the filter ends up doing a good job of modeling whatever the averaging does, but then that resulting filter might damage the peaks as well because they weren't part of the formulation.
Well, the peaks are part of the formulation of calculating the filter.
The original. Yeah, that's true.
So they will hopefully stay the same.
Oh, they are? Okay, so I see. So you keep that in the error signal.
Yeah.
I see. It's still in there. Okay, I see.
Yeah.
So you don't apply the windowing for when you compute the E signal. You use the entire thing in that case.
When you apply, when you apply the filter, yes, it's only when you do the averaging that you exclude it, so that you don't average, and then you get it back in.
Well, if you do analysis of this filter and estimate the frequency response, how it will like? High pass, low pass. That was the question.
Yeah, no, I understood the question, but it's.
You suppress more the upper part, the lower part.
I mean, it seems like you have this low pass kind of thing. That's your pitch periods, and you have this very high frequency noise. And so my guess is it's just going to be a high pass filter. But
yeah, but it's not really. I mean, it doesn't have any sort of high pass, low pass structure from what I've seen. It looks like a.
If you model the glottals as a series of Dirac pulses, they have a flat.
Yeah.
Frequency spectrum. And if you model the noise, which is closer to white noise, that thing has also flat frequency response. So where is the win here by applying filter?
No. Within a periodic Dirac, there's going to be a peak at a single frequency. So
no, it'll be a periodic a Dirac sequence of deltas in time will also be a sequence of deltas frequency.
Okay, right.
So you'd see a.
If your frame is longer, way longer than the period.
Yeah, that's right. Yeah. Oh, if it's a short frame, then I see what you're saying.
If it's a short frame, it's flat, and the noise is flat.
You're right. Yeah. Okay. I see.
Yeah, but the noise isn't really
just
flat.
get a peak.
I mean, if you look at it, the noise isn't really flat. It's to some extent this noise should have some relation.
It contain more low frequency. Then Mike is right. This is if you apply a kind of a high pass filter, you can improve the.
I see what you're saying.
Yeah. But it's not. I mean, so the noise isn't really flat in between. It should be.
If you have a filter applied to just 3 pitch periods, I mean, I don't know what the order of the filter is. But there's no way that's modeling any reverberation.
No, you wouldn't. Right? No.
So it's doing something that's helping reverberation, but it's doing it in some other way.
Yeah.
Right?
Yeah. No, it's not directly connected at all to this. But to some extent, these peaks here are connected to the reverberation, right? Because you sort of excite the room with That's
Right.
that's the way I see it. So every little clap of the glottis sort of excites the room to some extent.
I mean, maybe a different way to look at the question would be that once you do the averaging to kind of, get your signal into the nice type of residual that you want to see, you could actually estimate that G filter over a much longer window, right? There's no restriction that you need to do the G over a small period.
You could do it over a longer period, absolutely.
Then you might be able to actually get it.
Right.
Yeah. That's true. I haven't tried
I
that.
think
That'd be interesting to try.
That was me, definitely. I mean, the motivation behind this is that people that did this before, what they did was to try and somehow identify the peaks and then just flatten out whatever was in between.
I mean, and then I assume that you had this Gillespie citation, which I assume is
exactly.
like, not trying to look at the glottis, but just trying to say we want a peaky signal.
Yeah.
Right. That's the kurtosis thing.
Exactly. But even that actually flattens out the portions in between quite a lot when it works well. That's what I find. Because you just look at the peaky signal, right? So the ideal solution would be...
It seems like that's a little maybe be more robust because you don't have to estimate all this stuff. Like glottal closure instance.
No, it can be. But the problem is if your ideal is that you just have a peak and flatness in between, at best you get to sort of kind of robotic solution to the whole thing. That's the problem. So that's what I was trying to avoid here, is to try and sort of get back to the naturalness of the speech. Yep.
You're right, man.
So that's the overall idea here. So just to show you a couple of results of that, it's with 5 male, 5 female.
Does your group spend a lot of time on acronyms?
Sorry?
Does your group spend a lot of time coming up with acronyms?
Actually, we do, yeah.
Applaud.
This wasn't from our group. Applaud
okay.
was, I think it was done at UCL.
It's a general affinity, obviously.
We have a bit of, there's going to be a lot of acronyms actually along the way, so it's a good early point. Anyway, so we have the Applaud database with a bunch of 5 male and 5 female talkers. And this is with simulated room impulse responses with the image method with varying T60. And you assume that the talker is at about 2.5 meters away. So this is an output if you compare just the delay and sum beamformer on its own versus this SMERSH. Yeah, that's actually the acronym of Spatiotemporal Averaging Method for Enhancement of Reverberant Speech. So yeah, this is in terms of segmental signal to reverberant ratio. You see that you get some benefits over just the delay and sum beamformer.
So what's the order of the LPC analysis and of the G filter?
The LPC analysis is 13 here. This is for 8 kilohertz frequency. And G is 256 tap filter. So it's quite a long filter.
How are you guys measuring the signal to reverberation ratio?
So in this case, you just take the direct path, which is quite easy since it's a simulated thing. So I know that
whatever is left is your reverberation.
Exactly.
Okay.
That's it. So when it's simulated, it's actually quite easy to do. And also in terms of bark spectral distortion, which is something I used to use quite a lot, and supposedly should be closer to what we hear. So again, you see that there seems to be no. So you get more benefit when there's more reverberation from this than when there's nothing, when there's little reverberation.
Half a second. Get. You get basically 1 dB.
But this is in bark spectral distortion scores.
Can we see the previous?
Yep.
I'm guessing Mike's question. If not, I'm going to ask it.
Okay.
So here you're getting 2 dB.
Yeah.
So is that audible?
You can hear it actually, yeah. I mean, you can definitely hear the reduction in space. I have some samples on my laptop or something, so if you're interested in hearing them later. There's no point in playing. It wouldn't be audible. It wouldn't be audible here. So it's just. But if you listen to it on headphones, you can actually hear yeah.
Well, delay and sum is the least performing beamformer.
Yeah.
If you apply something more sophisticated, like let's say MVDR beamformer, which performs better than audibly better than the delay and sum beamformer, then what will be that difference?
I don't know. I haven't checked it. This is just compared to a delay and sum beamformer. Yeah, I haven't really looked at it.
Because it's repeatable, I agree.
Yeah. Yeah.
Question about your, I mean, I don't know, we can go on, but
Yeah.
so you had these, it seems like you did this study among other people, but you cited there's some self-citation there about
Yeah.
that the LPC coefficients or verbal speech are not quite as affected by
Yeah.
reverberation. Or the LPC coefficients of speech are not affected by reverberation.
Yeah.
Rather, something like that. I imagine that's, well, let's assume that's true. I could, this is a noise-free case. Right?
Yeah.
So in the real world, there's noise and speech. Generally, noise does mess up LPC.
Absolutely, yeah.
And so in the noise case, would you have to change something? I mean, if there's a room with noise and reverberation, we have to change, would this algorithm just work, or we have to change something?
Well, actually, you're right that it wouldn't, the noise does other things, but the way, in this case, the way I calculate the LPC coefficients is using multi-channel LPC. So you basically get all the correlation matrices based on the multiple microphones. So it's 8 microphones here. And that helps actually in noise as well. And actually, yeah, that's...
The beamformer would help.
Yeah. So you have either the beamformer, but actually I think when you do the multi-channel LPC, it's even better than doing beamforming first and then... So actually, yeah, you can hear that the interesting thing is that this averaging of the larynx cycles actually helps also reduce noise if you have it, because so that comes in there. So the combined effects you can hear quite well in.
One more question. So this is assuming that you know precisely where the source is for the beamformer.
In this case, yes.
Did you have a chance to do any sensitivity analysis to how error in that estimate and sound source estimate might
I haven't done, but we actually, a bit later after this came up, we implemented this and did some tests with, where we set up the whole system with, when you do an actual estimation of the source, actual source localization using just GCC FAT and things like this, and real voice activity detection and all this, and you get pretty close to these results as well. So, yeah, I didn't do any much further analysis of this. It was just an idea, and we tried it, and it worked nicely to some extent. And it was kind of fun to try it in a more realistic scenario. So it seems to perform more or less the same when you do that. So, yeah, okay. Great, so I'll move on to the next bit, which is on the channel estimation and equalization. Starting with this cross-relation between two channels, basically, which is often happen to be the beginning of multi-channel estimation. So all it says is that if you have an observation in you at one microphone and you convolve it with the second microphone's impulse response is the same as taking the second microphone observation and convolving it with the first microphone's impulse response. So starting from that, you can set up a set of linear equations with R being a correlation matrix and H all the impulse responses that you're looking at. And you can identify H by just finding the eigenvector corresponding to the smallest eigenvalue of R. And yeah, so this works really well if you have no common zeros between the channels and if the autocorrelation matrix of the source signal is a full rank. So that's the basic idea of this. And then you can continue with this and do an adaptive formulation, which is good, since acoustics change generally quite a lot when you move around, and trying to do it adaptively seems like a good idea. And by minimizing this error, you can get to something which looks quite similar to an LMS filter, and there's also other versions implemented of this. So this is all good, and it works well if your conditions are very ideal, but once you start having noise, this whole formulation becomes quite messy. So basically what your error function that you're trying to minimize does is it also tries to minimize two things. One is this original thing that you had, and the other one is this bit which includes the noise. And it's one of the causes to something which makes the convergence behavior of this filter is very strange. So you start converging, and then at some point it misconverges into something else. And it does this independently of how good your signal is, more or less, unless it's perfect. So you can see that even in things like 35 dB and 40 dB SNR, which is way too good for any realistic thing, it has this strange behavior. So one way we looked at trying to stabilize this is to add some constraints, some extra knowledge about what you're trying to estimate. And one of them would be to just assume that you know the direct path, say that you've estimated it from something else. So you add the constraint that you keep the direct path in your estimate as the correct one. Or another one, which could be, is to assume that your energy distribution in your room transfer function is uniformly distributed over frequencies, so it's relatively flat, and keep that as a constraint. So one of the misconvergence things that you see is that it actually produces some kind of extra filtering, and it makes the estimates sort of skewed here and there. So that's where this constraint came from.
K is frequency, or?
K is the frequency bin, yeah. So this would be the magnitude, the power of per band in the room transfer function.
Isn't this assumption that you have basically colorless reverberation there?
Yeah.
So pretty much this means that each surface is reflects equally all frequencies in the frequency band.
Yeah, more or less. Yeah, so overall it would be kind of flattish when you look at it, especially within the frequency bands that you look in.
With the image map.
Yeah.
Well, also I think in common rooms it's fine if you don't look at too high frequencies. So if you're within the telephone bandwidth, you'll be okay generally with this. So this was all done with sort of telephone bandwidth in mind. So I think it's fine. Yeah, once you start going into higher frequencies, then you get the frequency dependence, and it's different. But
and the low frequencies also.
Yeah. Yes, exactly. But yeah, so within telephone bandwidth, which is I think 8 kilohertz is still pretty hardcore for these algorithms to try and estimate the impulse responses in terms of the number of taps that you get. In either way, I mean, the idea is that you try and add some extra information about what you're trying to estimate, and you add some extra, basically it can result in an extra penalty term in your adaptation algorithm to try and control this. And if you take, it looks pretty much the same whichever constraint you take of these. You have this behavior which was without the, I don't know if you can see the plots here. So this was without the constraint, and then if you do have the constraint, it sort of stops where it should, although it slows it down a little bit. And here is what the channels look like for this case. You have 5 artificial channels. It's so each of these columns is one channel basically, and this was the original bit that we had that you're trying to estimate. This is what it looks like without any constraints, and if you do put some constraints in, it helps, so you get a pretty good estimation. But yeah, these are truncated to 128 taps, these channels.
128 tap reverberation.
Yeah. It's pretty short.
So, and the MCA, the red curve is
so the red curve is,
or is that
is the misconvergence. So it's at this point.
So how does it? What does it look like at the best point?
At this point, it looks like this. The problem is though how you find this point.
And stop.
And stop.
What's NPM?
Yes, I should mention. So the NPM is misalignment, but it's normalized. So
that's an oracle kind of.
yeah, it's used quite often. So it's the same as misalignment is used in normal channel estimation, but it normalizes so that you avoid any scaling effects. So if the channels are scaled differently from the estimates, it takes that into account. Yeah, so yeah, I mean, I have looked at some ways of trying to find where this point is, because that would be a good idea as well, is if you can find this and stop here, but yeah, it becomes quite tricky. Okay, so I think that's about the one I was thinking of saying about channel ID. It's still a very tricky problem, and to do it with very long channels, it becomes difficult. What I want to look at quickly is also say that you do have an estimate of the channel. What can we do to actually remove this channel from the reverberant speech? And the sort of original thought on multi-channel thing was this trying to equalize all the channels simultaneously using an equalizer G. And you have some desired output of what you want to get once you've equalized your channels, which is an impulse that can be with arbitrary amplitude and some arbitrary delay. And doing this, you can set up some least squares formulation on that, and you can calculate estimates of your inverse filters. So that's the fundamental idea, which sounds all good, but as everything else with this, it's full of, it can be full of problems. So one of the problems, of course, is even if you have a good estimate of your channels, you have several thousand taps in your channels. So you'll make the actual design of the filters very long. You usually wouldn't have perfectly known channels. You have inaccuracies in your channels, and trying to equalize this perfectly with inaccurate estimates, you'll get into a lot of problems as well. And you can also boost noise. So if you have noise and you have your channels, trying to invert it like this, it will also increase the noise that you had in the beginning. So one of the things I looked at was to try and do something about these two problems. So it was basically just quite a straightforward translation into the problem into subbands. So if this is the full band formulation of the equalization, so you have your speech signal going through the transfer functions, which you now know, and you design the inverse filters. You can just translate the whole thing by assuming that this whole thing happens in the subbands. So the only trick that is needed in this is to find the relationship really between the full band estimates and the subband estimates of the room transfer functions, and then you can design the equalizers. So you basically design and equalize in each subband separately, and then you reconstruct. So that reduces both the complexity quite a bit, and also it makes it less sensitive to some extent to inaccuracies on the channel estimates that you may have. So here's an example with how that works. You have, in this case, we had a GDFT filter bank with 32 subbands, decimated by a factor of 24. And with this setup, you get a reduction of about 120 in terms of floating point operations that you would have to design the filters. So it's quite an improvement. So here we have simulated a mismatch. So if you have an estimation error, it's just simulated by adding some noise to the true channels. And evaluate the outcome in terms of magnitude and magnitude deviation and linear phase deviation. So what you look at is if your how far your equalized spectrum is from flat, and how far your equalized phase is from linear. So this is the outcome of that, so this was done with 5 microphones, 4,800 tap channels, again simulated with image method, and this is results average over 100 channel realizations. So basically you have the room and you keep your microphone and your source at the same relative position, and you spin them around in the room to get various realizations of an impulse response. So you can see the circles are the full band version of the equalization in terms of magnitude and phase distortion, and if you do it in the subbands, you get some improvement. And you have system mismatch along the x-axis. So there's still an improvement, and especially if you go sort of above below minus 30 dB system mismatch, you can get quite decent results with this. And if you look at this in terms of the reverberation, just going back to repeat the same slide, but it's exactly the same setup as the reverberation was for Smursh, just to see what you could achieve. In this case, the impulse responses are, again, they're not fully estimated, so you assume that you know the impulse response, but you add some distortion to sort of simulate different mismatch that you get. And this is what you get in terms of segmental SRR, with that for different MPM, so different misalignment. So this one is the reverberant case. Then you have the beamformer. So this is the delay ensemble beamformer. This just as before. And these are with a progressively better estimation error of the channel that you would have. You get better reverberation. And so yeah, if you had a perfect channel and everything was great, you could actually achieve pretty good results. But even down here, at sort of 0 to minus 30 dB, you still perform quite good with that. And in terms of Bark spectral distortion, it's pretty much the same. So again, this is the reverberant delay some beamformer, and here are all the versions where you see that anything above below minus 30 dB misalignment, you get pretty good audible results, and it's something you can hear as well. So just to conclude that part of the talk of, yeah.
You know, if, like, just trying to get a sense of the realisticness of using all these techniques. So if I am here and I talk to the microphone and I move my head, 6 inches to the left.
Yeah.
How much, give you an idea how many NPM, dB of NPM between those two filters would there be?
I don't know it in terms of NPM, but I know that even if you move very little, trying to equalize with what you had here already can provide quite a lot of distortion. But I don't know in terms of NPM exactly what it is.
So it seems like by the time you figure out what this filter is, unless the person's really staying still, the chances that it's...
Or it's artificial mount, or it's simulation.
No, right, I'm saying, but in a real scenario, it seems...
In a real scenario, yeah, it's very difficult, and that's, yeah. That was, so as I said, this was one part of my PhD work, and one of the conclusions that I did get to is actually that I think this is nice because it gives you hope that at some point you might be able to actually do perfect reverberation. It's there in a very artificial scenario, but at the moment, the way things work, it's not really possible because, yeah, you need to be able to track the impulse response within seconds, less than seconds. So, yeah. So I think in general, between these two algorithms, you have on one end of the spectrum is merged, which gives a little bit of the reverberation, but you can actually implement it on a computer and it would do something. And then you have this blind system identification and equalization, which potentially can give you really good reverberation. But at the moment, yeah, you need to calculate for a few days at one location or something to actually get something out of it. So, yeah. So I'm going to move on to the next bit, which is intelligibility estimation. So I have until 12, right? That's, yeah. Okay. So just with a bit of background, intelligibility estimation is, what we're trying to do is, going into noise now, is to find the relationship between SNR and how much you can understand of what is being said.
Be a human being.
In my case, it's human being, yes. Yeah. So, yeah, this stems from the project that I work on now. And so the question is how you estimate this. Of course, one way is to have automatic estimation. So that would be really good if you can have things, and there are some methods to do that. Some which are intrusive. So intrusive estimation means that you have the clean signal and the noisy signal, and you can plug them into your algorithm and it gives you out a number. And then you have the sort of oracle of everything, which is non-intrusive, where you should be able to just give it the noisy signal and it gives you out a number of how good the intelligibility is. And there's quite a few methods out there for intrusive and very little for non-intrusive. There's been some recent attempts on that, but not fully verified yet. And then it's the subject-based estimation, where you instead have listeners, people sitting there and listening and somehow indicating what they hear. So in that case, you can have two ways of looking at it. One is that you fix your SNR for a noise thing. So you place samples at a fixed SNR and you count how well these subjects understand what's being said, and you get out the percentage of correct recognition. Or you can have a variable SNR and a fixed performance that you want. So you set and you say, I want to find the SNR for which the recognition rate or intelligibility rate is 75%. And then you vary the SNR until you find the right spot. And that is, so this constant stimuli version, where you fix the SNR, is quite slow. And this one is somewhat faster. And in the work that we were trying to do, this subject-based variable SNR is what we went for and what we actually needed. So I'm going to talk a little bit about that. So the objectives of what we were trying to do is basically trying to assess the effect of speech enhancement algorithms on the intelligibility. And also to maybe see if there are safe regions of operation in these methods. So if you have, if somebody gives you a speech cleaning algorithm to tell them, does it harm intelligibility or not? And often you get the speech enhancement algorithm with a slider where you can adjust some parameters. So you can try and look at the parameter space and see if there are some regions in this parameter space where it could be relatively safe to use this. Now, although these automatic estimation algorithms exist, they're good at estimating the intelligibility of speech in noise when nothing else has happened, so it's just speech and noise. But they're not very good at predicting what happens after you've processed the speech. So that's one of the other problems, and this is ongoing work to actually try and come up with good automatic methods to predict intelligibility for speech enhancement methods. The subject-based methods, on the other hand, for this type of problem result in a lot of people having to listen to a lot of data which takes a lot of time, and if you pay these people, which you should for ethical reasons, it gets quite expensive. So we needed something that you can do quickly with people, and let's see what, yeah. So this is the basic procedure of this adaptive test for intelligibility. So in general, that's what you do. You have a trial, at the trial end, you present the listener with something, a sample, and the listener has to indicate what they think they heard, right? And you present this at a certain SNR. The listener that says in one way or the other indicates I heard this or that, and you score that with 1 if it was correct or 0 if it wasn't. Then you take this knowledge, you have the knowledge of your SNR and what the subject indicated, and you have to adjust the SNR somehow to present it back to the subject. And typically this would be what people use is a fixed step size way of doing it. So you basically say your step size is 1 dB, and if you're looking for intelligibility performance of 50%, you play the sample, and if the subject is right, you decrease the SNR by 1 dB, and if the subject is wrong, you increase it by 1 dB. And at some point, you will converge to, hopefully, to something which gives you 50% intelligibility point in terms of SNR.
Are you just giving one probe and getting a response, or are you doing an average over?
No, you have to do an average over quite a few. So that's the whole point. So yeah, because you don't know what the SNR you're looking for is, so you have to start somewhere arbitrarily.
Oh, no, I meant that. So let's say that right now I'm at SNR equals 2. Then are you giving like 10 probes to the user at that point and then averaging to get their performance rate, or are you just doing 1 and getting back a single response?
You get, well, it depends a little bit on the data. In our case, you do 1 and you get a single response. So you do, yeah, and then you can step after that. So really, actually, the question is that I'm getting into is how to best adjust the SNR at each probe so that you quickest get to the right SNR for a given intelligibility. That's really the fundamental problem here. And one way to try and do this is to look at something. This is something called the psychometric function of the speech, which is quite commonly used in psychometrics and psychoacoustics. So basically, this is what the relationship between SNR and intelligibility looks like. You have a sigmoid function which links the two. And that sigmoid function has kind of at the point of intelligibility that you're interested in, say 75%, you have a slope of that function, and you would have a threshold, which is the SNR. And also there's shifts and scaling. So, for example, you have this one, which is the guess rate. So people can sometimes guess the right answer, depending on how many options you have. And you have the lapse rate, which is basically a point when you should hear what's being said, but you don't because you're thinking about lunch or something, for example. So starting with this thing, we use this background model rather than just doing a step-by-step adjustment of the SNR, is trying to select the SNR so that we get the most information about the underlying psychometric function at a given intelligibility level. So you can take the psychometric function, and with all these parameters of the lapse rate and the guess rate. So you have the gamma this, and then this is your sigmoid function, and you can take more or less anything which represents a sigmoid function. In this case, we use the cumulative normal distribution function, which is a nice sigmoid, and basically the slope and the threshold of it are controlled by the mean and the variance here. So now trying to estimate this the underlying psychometric function is really just by estimating the mean the variances of that and find where it fits best. So using this as the background, what we can do is say, well, select the next SNR value of the next probe so that we minimize the variance of the slope and these threshold estimates, right? And just to briefly sort of go through how we do this, you start off with a two-dimensional PDF, where so you have the slope and the thresholds for all possible psychometric functions. You initialize it. You initialize this PDF to something. In the next step, you can calculate the probability of getting a response R at a certain SNR. Then you estimate the posterior probabilities for each of these psychometric functions that you have underlyingly. And using this, you can find the variance of these two parameters, alpha, the parameters of slope and threshold, and also the expected variance that we were looking for. So then you basically select the next SNR that gives you the smallest expected variance for the estimation of the two parameters. Then you present.
So you don't know that the probe will be. Oh, I see. You're looking at either if it's a 1 or a 0.
Exactly. Yeah. So you check both. Yeah. Exactly. Because you don't know what it's going to be. The answer. So what you do then is you present it. You present it to the listener. You get the answer, and then you update your PDF based on the answer and the SNR that you tested with. And yeah, this is called BASIE. Speaking of acronyms, it took a while. So that's the idea, and in this way you basically get the quicker. The idea is that with this one you should get a quicker estimate and more accurate estimate of the SNR you're looking at. So the other thing, sorry, yeah.
So can the argument, can that be solved closed form, or is that just you pick a bunch of SNRs and find the one that minimizes that?
At the moment, I just pick a bunch of SNRs and find the one. Yeah, exactly. And actually, I didn't add that on the slide, but in practice, we also resample and rescale the PDF at every iteration so that you get closer to the actual one. It's quite, I'm not sure with the closed form because you need the inputs of the people. So,
I imagine it was going to be gnarly to have those CDF expressions.
No, it's because it's more of an adaptive filter with the subject, with the person sitting there. So you need this interaction. You just have this underlying model of the person that you're trying to match.
What I'm saying is you could
choose the next probe point.
Depending on what the form of E of variance of blah was, you can just take the derivative of that expression with respect to x, that's 0, and find x.
Or you could use something, if it was smooth, like if you had a logistic instead of using this.
But it seems like
you could probably,
actually,
convex formulation. In fact, it might even be quite convex in this case. It's not clear that you actually need to just sample a bunch of points. You might be able to use, a Newton method or something.
Yeah, maybe. I haven't looked at that yet, but that's one of the ideas to also look at the logistic function to see if you can get better stuff.
And one thing that might be interesting is that, I would suspect that what you're doing is fine because I expect that bound is probably going to, if you took steps of 0.1 dB and then you look with it around that to see how much variation you'd get in the bound based on a small movement, it probably wouldn't be that big a deal. Yeah. So it probably just sampling a bunch of points, it's probably pretty smooth, I'm guessing. I don't know if you've looked at that.
Yeah. No, it looks, it does look smooth. But so, there was,
So a question about that. Though. So then, so you're saying that you choose a bunch of points. Are you changing the sampling of that? So maybe you do it at some fixed, 0.1 dB steps or something like that. But do you change the spacing of that grid as you move along in your algorithm, or is it always the same?
It's always the same spacing, so I don't change the spacing. Yeah, it's a fixed.
Some fixed kind of sampling along the entire from 0 to 1
exactly.
or whatever your range is. And
So you need to sort of fix the ranges as well with the SNRs. So yeah, but normally it's quite reasonable to fix it. Yeah, you can have a pretty fine grid, which is more or less enough. I mean, you'll never really get that accurate estimates based on the humans anyway. So. Yeah, and then the other bit which you could do with this is, of course, you can make it estimate more than one psychometric function at once, which is, I'll show you later why that's a good idea. And yeah, actually, so the idea of this estimating more than one psychometric function is that you can simultaneously estimate processed and unprocessed speech with one subject to try and speed these things up. And it's also, while doing this, you're playing samples to the listener which have been processed and which have been not tampered with. So it sort of helps with the attention and keeps the listener happier. That's one of the thoughts that people have had.
So what would be the workflow in that case? So they would hear like, type 1 sample and they'd give a response, and they'd hear like type 2 sample and give another response?
No, so that's the next point actually. Oh. The answer to your question is that you choose which sample to play, which gives you the best minimization of the cost function that you have.
So you're choosing now not only between SNR points, but also which PF you're choosing at every point.
So if you've already converged very quickly with one of them, there's no point in playing back samples on that, right? So.
But is this why? But it seems like these could be completely independent problems. Like, I mean, does it make a difference to?
No, it doesn't make any difference to.
Just serialize them and do like first PF1 and then PF2.
You could do that, yeah, exactly. The only difference it makes is that there's no point in collecting more data if you know that you've already converged quite well. So if your error is minimized, then there's another. So if you have two conditions, unprocessed and processed, right?
So
for instance, then if you've done quite quickly, if you've got to the right point quite quickly with the processed one, but the unprocessed isn't, you want to use more time to try and converge with the processed bit. So that's the only reason. But it doesn't actually do anything else to the
They don't really help each other.
No.
Okay.
No. They only help. The idea is that by interleaving samples in some kind of. Yeah, exactly. That's the idea.
Okay.
Yeah. So here is just one example of a simulated version of this BASIE. So this is just to see that it works if your underlying model is correct. So this is simulated with the psychometric function model. So you just do the inverse of that and you generate user responses that are correct. That's the idea with this. And it's compared with a fixed step size of 0.5 dB, which is pretty good. Normally people use around sort of 1-2 dB step sizes for these. And it's averaged over 500 runs. So here is the BASIE one. So you can see here is the number of trials that you run, and here's the threshold estimation bias that you get. So you can see that you get pretty accurate estimation pretty quickly with BASIE, but with the fixed step size, you're going to have quite a large bias, and also the variance is pretty large with the fixed step size, something you can't get away from. So.
Surprised with the fixed step that I would have expected to kind of more jump around back and forth across the zero bias point. Like, why is it always? Because I mean, like if you go with the fixed step procedure as you described earlier, you're kind of like you're giving a probe, and then the person says something, and you take a step, you give a probe and they take the step. And so like, you know, you can see how that would result in continuous jumping around, but I'm surprised that it's always biased in one direction here. Do you have any thoughts about why that?
I think, I'm not sure exactly why. I mean, I think the reason is probably that you have a very ideal user which does something strange with that. So it might converge, because if you look at it, because it's similar, so in reality it wouldn't be like that. In reality you do get actually those jumps that you're talking about. So this is really with a very ideal user. So in some sense, BASIE is more suitable to test with this ideal user because it's trying to estimate exactly that function, whilst with this fixed step size, when you do that, you don't really necessarily have this underlying assumption of the threshold. So, I mean, one of the main things what I wanted to see with this is how many trials you need to get some convergence as the minimum, which is satisfactory. And the answer was that you get it at around 30 iterations. You get an answer which is sort of between plus and minus 1 dB, which is usually good enough for estimation.
What's the model? So I guess one thing that had not clear to me about the simulation here is that what is the model for the human response here? They'll just respond at exactly the probability that the model says. So if you're, okay, I see. So you have like this sigma and you're saying, you know the model is correct. You have some parameter set that you have predefined for the simulation. And then you're saying, if they'll report with 70% accuracy here, then they just report with 70% accuracy and you just sample from that.
Exactly, that's it. Yeah. I see. So it's a very ideal condition for BASIE. That's it, yeah, exactly.
And this still says, this assumes sort of single user.
Yeah, well, yeah. It's, because you have one model, so it doesn't really incorporate anything that are more user-specific than that.
So one trial is typically what, a phrase?
So, well, that's a long ongoing discussion in this community that people do this, is what one trial is. So it can be a sentence, or it can be a word. As I'll mention a little bit later, the thing I was using for a while was digit triplets. So you hear three numbers, and then you have to enter the three numbers that you heard.
So it's a 5-10 seconds. By 30,
it's quite quick.
A couple of minutes, yes, you can get the measurement.
Yeah, exactly. That's the idea. So I'll show you how you can use, how I use this for evaluating a couple of methods. Yeah, so this is where it actually goes to when it was applied for estimating intelligibility. So this interleaved bit, it doesn't really help, as I said, with the estimation in any way, but you can sit down one user and he does one trial and you get information about several different settings, for example, in one algorithm or any other thing. So you could have, because actually this you can apply with anything. All you do is vary the noise, and you can have reverberation in the background, you can have a codec after the noise. So I've looked at various things with this. So, you know, the noise is just a variable. And very often it's a very sort of decisive variable. And the way we measure this is something called, well, it's not called, I've called it relative tolerance to added noise. People call this kind of different things, but what it means really is that you look at this threshold SNR for the noisy speech and the threshold SNR for the processed one, take the difference, and that gives you sort of the tolerance. So if you have a positive RTAN of 1 dB, it means that you can lower your SNR by 1 dB and still get the same performance in intelligibility. So that's really the whole thing. And this is how people were using this. So it's digit triplets that they were using, and you have an interface. So you listen to stuff and you just enter your three numbers. Yeah, there's a long talk just on how you would actually select all this, the data that you're going to listen to, but I'm not going to go into that. So here is a relatively small study with this, but it's just to sort of demonstrate what the idea was. You have 6 people. The samples, these digit samples were normalized, and you have car noise in the background, and people listen to this with headphones. And we tested this with noise reduction from a commercial audio workstation, which I won't mention which one it was. It's not good. And just standard spectral subtraction with minimum statistics, noise estimation. And to choose the parameters, so this commercial audio workstation tool, for example, has 5, 6, 7 parameters that you can vary, but actually the one that makes most difference when you listen to it is the maximum amount of noise reduction that you apply. And also it is similar with the spectral subtraction. That's where you can really hear things happening. So I took a bunch of settings for that, between -1 dB, so you have hardly any subtraction that you can hear, to -40 dB, where it really tries to destroy everything. And if there were any other parameters in this algorithm, just keep them fixed to whatever was recommended. And so, yeah, so this is really pushing it to 150 iterations. So you do 150 presentations of these samples to the people, which include the estimation of all of these things, which is pretty quick. So it's 10 minutes. Yeah, and you get quite a lot of information in 10 minutes from one person, which is pretty good. And this is the outcome of this. So really the absolute values here are maybe not that important as the highlight of trying to, well, first of all, generally the spectral subtraction and this one as well, they destroy intelligibility quite a lot straight away, even with small settings. It seems like, yeah, there's quite a large effect on intelligibility. But this commercial system one is definitely has a very strong effect. And I mean, you can hear it, that if you set this parameter to -40 dB, of course I don't know this maximum noise attenuation. I know what it means in this, because it's a MATLAB implementation, and I know what I've done in there. With this one, I have no idea what this means. So anyway, when you do it at -40, it destroys more or less anything that you can hear.
So positive R10 is when it's making things better, negative R10 is when it's making things worse.
Exactly, yeah. So I've highlighted these 2 things here, which are the positive R10s.
These are all, the original SNRs are all like very negative.
Yeah. Well, you don't know the original. So this R10 is actually the SNRs. So you vary the SNR all the time, right? So.
Well, what was your range?
Well, it goes between 10 dB, plus 10 dB to -20 dB. Because what I'm looking for here is 75% intelligibility. So for car noise, for that you need to be somewhere at I think it's -11 dB or something like this, to actually get, unless it's a very good car.
Did you count R as one? Did you take all 3 digits correct, or how did you do? Like, correct is all 3 correct, or correct is digit of the tryout? Did you count the sentence accuracy or the word accuracy?
No, I did all 3 digits. So all 3 digits have to be correct. Yeah.
So let me make sure I understand what you're doing. Because I mean, so it seems like, okay, so you had in your formulation you said that, like, okay, I have a target which is like 70% recognition accuracy,
yeah.
Right? And then your R10 is measuring that, like, okay, if I care about having that 70% recognition accuracy,
yeah.
there's the number of dB I can drop in the process case, exactly. And still have this thing.
That's it.
So an alternative way to look at it, I mean, and that makes sense. I mean,
yeah.
I think that there's value there. But I mean, but one alternative way you could say, so the thing is that, like, there would be a different chart essentially for each target recognition rate that you had. Like, if you said that, okay, now I care about 80%, accuracy and intelligibility, 70%, then it's a different chart.
Yeah.
And I wonder that, like, so let's say now your manufacturer, wants to kind of characterize the system or something like that. Like, an alternative way would be that you could say that, like, in each of these settings of dB, I actually just measure, instead of R10, I measure the actual intelligibility rate, in each case, because then you have a fixed table. I mean, it's not as good in some way. I'm just curious about your. Do you see what I'm saying is the alternative?
Yeah,
like,
yeah.
I mean,
so basically, you keep fixed SNRs, and then you measure the...
Fixed SNRs, like you just walk through the SNRs you have in your table, and then you say that, like, well, you know, given this, what is the intelligibility rate? I'm just curious as to your thoughts around, because I like what you're saying about the R10, but I wonder what your thoughts are about, like, you know, doing R10 versus just measuring like a fixed, you know, sensitivity rating, what the pluses and minuses might be of doing that.
So if I understand you correctly, is that, yeah, is really looking at the other alternative is that you have the fixed SNRs, a bunch of SNRs, and you measure the, I mean, yeah, so first it takes longer to do it. Okay. The second one is that you wouldn't really, it's kind of difficult to know what SNR range to look at, right? So in this case, you actually, yeah, I mean, it's easier to know what intelligibility level you're looking for than knowing what SNR range you're looking into. Because the SNR range will change.
I mean, there is this psychometric function, right, which gives you a ballpark. I mean, I would almost think that that's a prior, right, on a prior distribution on what these thresholds would.
No, but they change for every noise type. So the intelligibility level.
Usually?
Yeah, quite. So if you have bubble noise, for example, to get 75 dB intelligibility, you have to be somewhere, well, in the vicinity of 0 dB. Sort of minus 5, 6 dB, I think it is. And if you have car noise, you can be down to minus 12.
I misunderstood one part of your table. So I see. So this noise attenuation, that's a setting in the algorithm.
Yeah.
Oh, okay. Right. So given a setting in the algorithm, then you're looking across a bunch of different noise. Oh, okay. Sorry, I missed that part. Sorry, I thought this was just a fixed source level of noise that was in your source. Yeah. I see. This is just the
no. So basically, you change the setting of the algorithm, and then you find the SNR for which your intelligibility level is 75.
Across a bunch of, I see.
Yeah,
okay.
So, exactly.
So I think it's kind of known that speech enhancement algorithms don't improve, which are kind of proven, don't improve intelligibility.
Yeah.
I think that's sort of a known.
No, I wasn't trying to prove that at all. Yeah.
Right, well, I mean, but you kind of have, right? Yeah. And so, but there are speech processing algorithms that claim at least to improve intelligibility, like I know, like these binary masking things, and there's other things, you know, like this, like Philip Loiseau's group is a big proponent of people who work in this space. So, have you tried? It would be interesting to see if you could verify something that correlates with some published result, like with a positive outcome rather than a negative outcome.
The trials I've done is something that. I couldn't present here, but I have correlated it to, so I've correlated this way to do really more robust intelligibility estimates. So there's actually, this is quite a weak test for intelligibility, but it's fast. So another way to do it is you have a listener who listens to a whole sentence with keywords and so on and so forth, which is, Loiseau does that a lot with his tests. And I know that for spectral subtraction and a few other algorithms, we definitely get really good correlation between this more rigorous test and this simple test. We have actually looked at some of Philippe Loiseau's methods and tried to reproduce some of the results, but we haven't really been able to get this intelligibility improvement that he claims, to be honest. Yet. Although, yeah, I mean, binary masks, for example, they can, you know, if you have the ideal binary mask, you can easily demonstrate something which sounds really good, right? Because you have this oracle and it sounds fantastic. And it's clear that you do improve intelligibility, but to actually do something with it, it gets tricky. I haven't because, it's because of the nature of the work that we've been doing. We've tried different things.
So one other question. There's a subtlety here around how you might average over users, right? Because are you just like taking the scores of all users and just taking the mean and variance for each, or are you doing ANOVA?
In this case, it's just the mean and variance, but we tend to do it ANOVA when.
Yeah, because especially this one, right? Because so let's say that you have listener A and listener B, and listener A just kind of has crappy hearing, and listener B is good, right? You want to kind of account for that in the variation, so that.
No, in general we do that. So
okay, you do.
Yeah, this is as I said, this is just a case to sort of demonstrate what we're trying to do. But yeah, in reality we have many more listeners and Exactly, yeah. So
So far from speech
I'm sorry.
So far from speech enhancement.
well, so yeah, that's so basically just to sum up that part is the presentation of the BASIE tool, which can help you estimate the intelligibility relatively quickly. In about 30 trials, you can get an accuracy of ±1 dB. And I showed you how you can actually use this to try to search in a sort of space of settings with subjects relatively quickly. So thank you for listening.
Do you guys have more questions?
Yeah, I have one.
Go ahead.
So one question is, I really like the second one. I think that's quite interesting, the adaptive approach. And it seems that at this point now you could say, oh well, we don't want to use the digit test. We want to use more the stronger sentence-based keyword test. You can just slip that into your adaptive framework and everything's fine. But one question I was going to ask is, what do you know about, or can you characterize how good that model is? Like that, that particular sigmoidal model using the normal, the integrated normal. Are there measurements or is there evidence that shows that is a really good model across a variety of situations to use?
There is quite a large amount of literature on that. There's a vast amount of literature on intelligibility testing. So it looks like it. And actually the other thing which we looked at, which is less obvious, is if you have a signal processing algorithm, would it just shift the whole psychometric function if you have an improvement, or would it act differently in different parts?
Yeah, so that's a good question.
That's to sort of raise a question myself.
Yeah, that's okay. That's the wrong answer. Now you've made your life more difficult. Right, because you could have a certain kind of algorithm which now effectively changes the shape of what.
Yeah.
But that is, that's very typical. Some things that improve very low SNR can be high SNR.
Right. But then that sigmoidal model is no longer the right one.
Well, I didn't say that.
Correct.
So actually, the interesting thing is that
it's just not a linear shift of the model. It's some other weird one.
Yeah. Well, I mean, but it could be different, right? Because it could be the case that something, like it might not be monotonic anymore, because it could be the case that. Let's imagine horrible algorithm G, which is really great under a certain level of noise, but if things get too clean, then it actually does worse, and then you could have a shape that ends up being quite different.
Yeah, but so far what we found actually is that, doing this with more rigorous testing, we actually found that with quite a few of the standard sort of speech enhancement methods that exist, there is just a shift. So far, so good. I haven't seen any evidence.
He's talking about -11 dB.
Yeah.
For in-car environment. That's relatively rare conditions, actually.
No, that's okay. I mean, it's just that and you don't have. It doesn't even have to just be a shift, right? Because you're modeling both the mean and the variance, so you have those two parameters to move around. But my concern was just that if there were some algorithm, there may not be. I'm just maybe positing, something that doesn't exist. But if there were something where the actual, overall profile, of the response with respect to noise levels changed completely, like if it actually got worse, under low noise, right? Then you might no longer have this thing. You might actually.
Yeah.
I mean,
But maybe such a thing is.
But you're still looking, in some sense, in defense of it, is that you actually just, although we have the whole model of the function, you're still kind of looking at one point. So I don't know what the answer is, but you look at some kind of slope. So that shift, I'm not sure, but it's.
One thing that I would say that another thing that I would say which is good about your method, which you didn't highlight, but maybe you should, is that so if you believe the model, right, and you do your adaptive thing, right, you're not just getting a point, right?
No, exactly.
You're actually getting at the curve. So one thing that I would say is that that you could argue, and I was wondering if you would say that when I asked the earlier question, but you could, but maybe you feel like it would be reaching too far. You could say that, how I was asking that, if I changed my threshold, it would be a whole different chart.
Yeah.
You could argue that if you fit the model well, you could just create that new chart without running any more samples because you've actually modeled the entire curve.
No, exactly. Yeah, that's right.
So
That's it.
That's a great benefit over,
it is.
over
It is.
any kind of, you know.
I didn't talk about much about the slope estimate because I don't really use it for anything yet. But yeah, that's another good advantage of this, because if you do the fixed step size and if you didn't need the whole curve, you have to sort of sample a few points along the curve, which is basically to some extent what you said, and then you can sort of fit.
I mean, there is an issue of, like, you know, you could argue that, you're right. I mean, so because you're focusing on that point, you might only be really valid around that region and maybe not so on other places.
Exactly.
I see. That's what you're saying about the fact that you're marking this region too. So if this curve is valid only within that,
Exactly.
the neighborhood of where you care about, that's all that really matters.
Yeah. Because what could happen is that if you have this algorithm, you can still be valid at the top, and then this kind of some
The
distortion.
problem is that I mean, I think your setup might be convex-ish right now, but then if things were really weird, right, like, you know, you might end up in some state where there might be multiple places, you know, which would satisfy your local constraints, and then you could have some ambiguity.
Yeah. No, it's very tricky, and once you have humans involved in it, it's quite difficult. But yeah, and the processing. But I think so far it's been fine, and you know, so far the only evidence that we do have from a lot of people is that this model actually holds.
Yeah,
so
the other thing that might be interesting, maybe I'll save it for now. That's fine. Go
You
ahead.
have your 1 hour this afternoon, I believe.
I'm going to stop talking. Mike, go ahead.
No, I'm done. I'm saving it.
Oh, okay, all right. Okay, good.
So, you guys will have the opportunity this afternoon. No more questions. Thank you, Nikolai.
thank you very much. Thanks.